Saxon Algebra 2, lesson 39. We have a little algebra and then a splash of geometry in this lesson. The algebra piece is called the difference of two squares. And we talked about this last year. If you have two numbers that are perfect squares and you're subtracting them, you can automatically factor it like this. You can factor into two binomials, subtracting the roots of those numbers first and then adding them. And obviously you can put these in either order. You can remember this either way you want, as long as you remember that one binomial has a plus and the other binomial has a minus. Now, John would like to prove to you that this is true. So what we're going to do is we're going to look at these two quantities together, and notice that the first term is the same, the second term is the same. The only difference between them is the sign in between. Notice that the first sign is the same. Both A's are positive, okay? This pair of quantities is called a conjugate. And it's defined exactly by what I just said. Same first term, same second term. The sign in between the two terms is different, right? One's plus and one's minus. What happens when you multiply conjugates is something very cool. So let's just multiply this. We're just doing the dance in the dancing room on Saturday mornings with the kids, the 10-year-olds, the 11-year-olds back. It's like 1930s, right? The sunshine is trickling in and we see the motes of dust in the air. There's mirrors around the room. Everyone's kind of awkward and shy, but we're gonna dance. A times A is A squared. A times minus B is minus AB. She's done, her turn. B times A is plus AB. And then this is minus b squared, right? There's the minus. Look what happens when we add. That cancels, and we get a squared minus b squared. This is how I can prove to you that this is correct. It will always be this way. I multiplied the same two quantities, and I got this in the end, all right? So that's how I can prove to you that the difference of two squares works. Using it in operations is pretty straightforward. Again, I'm quite sure we did this last year. It says solve this by factoring. Okay, we look at this and go, no, that's a hot mess, right? We're used to seeing trinomials. We're used to seeing an x squared and then an x and then a plain number. We can handle a number here and use the man-eating dragon, you know, right? Because it doesn't matter if we have a number out here for the man-eater. We just do A, B, and C. But we don't know how to deal with the lack of X. Then something in our brain flips. That's the hard part. And we realize, oh, this is a perfect square, and this is a perfect square. So what we do over here is we say, okay, if this is the pattern of a squared minus b squared, then let's find the root of each of these terms, and that is what we will define as a and b. So the square root of this would be 2x, and the square root of this would be 3. Now we can write this a minus b times quantity a plus b. Again, doesn't matter which order the plus and minus are. And now we fill in with what our problem has for an a and a b. 2x minus 3, 2x plus 3. But this is an equation. We're not just factoring, we're solving. So this tells us, using the zero factor theorem, either this is equal to 0 or that is equal to 0. So either 2x minus 3 equals 0 or 2x plus 3 equals 0. And now I'm going to do some mental algebra. I'm going to change sides. That becomes positive 3, and then I'm going to divide by 2. So x equals positive 3 over 2. That's what this one leads to. Over here, I'm going to do the same thing, but I'll get a slightly different answer. I'm going to have to subtract. So it'll be minus 3, and then I'll divide by 2. So it'll be x equals minus 3 over 2. 2. And there are our answers to this problem, all right? So the trick in recognizing these problems is seeing, oh look, they're 2 perfect squares. And now I can use this pattern for factoring, and it's as easy as pie. Okay, we have one more of these. Example 39-2. Solve 81 m squared minus 25 equals 0. And again, we have that moment of sheer panic when we go, what? Those numbers are big, I don't like them. I see a squared, but where's the rest of the quadratic equation? It doesn't look right. And then we go, oh wait, times tables, 9 times 9, 5 times 5, and look, that's m times m. Got it. And we're ready to factor. This will be the A, this will be the B. I really put my little foot down. My foot's not little. Put my foot down and say you need, if this is the squared version, then you need to find the square root of each of those so that you can then set up the pattern for the solution. So the square root of 81m squared would be 9m. The square root of 25 would be 5. Now we're ready, and this time I'll just switch it up. I'll put the first quantity with the plus and the second one with the minus. It doesn't matter. And we'll get 9m plus 5 times 9m minus 5. Those are both quantities. And then this is an equation, so I'll set it back up equal to 0. Now I'm ready to say that either 9m plus 5 equals 0 or 9m minus 5 equals 0. And I do a quick little blast of algebra on each one, and I get m equals minus 5 over 9. And this one, I'm going to end up with a positive 5, also divided by 9. And these are my 2 answers for this difference of 2 squares problems. Isn't that cute? I think those are fun. I like difference of 2 squares. I will say this, very often what happens to students is that because they're relatively straightforward, we don't spend a ton of time on them. And then when a problem shows up later on where we need to do difference of 2 squares factorings, students often forget and are like, I don't know what to do with this. And then I have to go, oh look, perfect squares. And then they go, oh, I vaguely remember. So put this into an important place in your brain so that you'll be able to use it. Now let's talk about parallelograms. I know, they're not the most fascinating topic. Parallelograms are 4-sided objects, so they are quadrilaterals, but they have 2 pairs of parallel sides because these guys are parallel to each other and these guys are parallel to each other. I want you to pretend that you're 4 years old and you're playing in a refrigerator box. And somebody, maybe your dad, has come along and has opened it up so that it's a tunnel that you can crawl through. And so you and your siblings and a few friends have been crawling through this thing over and over and over again, having a wild old time. And it's tipping. That's what a parallelogram is. Just think of it as a box that is tipping, and you will always understand. Now, these 2 sides, these sides opposite each other, will always have the same length also. That's what this marker means, is that these 2 have the same length. These sides have the same length as each other, not necessarily all 4 of them the same, but the parallel sides are the same length. Now, here's another cool thing. The sides, the angles opposite each other, just a second, I'm going to write these as words. Parallel sides are the same length. That's my first rule. My second rule is that opposite angles are equal. Let's just make an equal sign. Okay, so these 2 guys are the same. And these 2 guys are the same. Let's put markers on them. Those are the same. And these are the same. Okay? The third rule is that adjacent angles next door neighbors. Adjacent, I always think next door neighbors. Adjacent angles add to 180 degrees. So that means in this case, one of these angles plus one of these angles equals 180. And the fourth one sounds weird, but it makes perfect sense. The diagonals bisect each other. What on earth does that mean? Let me switch colors so you can see it a little bit better. If we draw a diagonal from here to here, and we draw a diagonal from here to here, we can see that they're different lengths, right? This one's a lot longer because of the way the box is squished, right? But what's interesting is that these two lines chop each other in perfect halves. So this line chops this line in half, meaning this segment and this segment are the same size. And this line chops this one in half, meaning that these two are the same size. They're not the same size as each other. These are not the same size as these, which we can see because this is a whole lot longer. But each half of the line matches to the other half. All right, we're going to use these rules in just a momento to do do a problem that has an algebra in it. That's fine. And we just have one more problem, just so you know. Now, a rhombus is a parallelogram that is special in 3 additional ways. All 4 sides, I'll draw a picture in just a second. Just let me write first, and then I'll draw a picture to show you what all this means. Okay, let me back up just a little bit and draw you 2 boxes. When you played with this first box that was called the parallelogram, right? I'm back into talking about cardboard boxes again. Parallelogram. This was from a refrigerator. So it's not square, it's a rectangle. It's a squished rectangle. Okay, but when your family got a new, maybe a washer or a dryer, this picture isn't going to be perfect, but pretend. A rhombus is the same on all 4 sides. It's a squished square. Okay, so all of the things about the parallelogram that we talked about on the last page, all of those are also true for the rhombus, but there are 3 more things about the rhombus that are also true. The first one is that all 4 sides are the same length. Oh yeah, it's a squished square, so that makes sense, right? That a square has all 4 sides. So just because the box is squished doesn't change that. The diagonals bisect the angles. Okay, what does that mean? That means that when we divide like this part is the same as this part. This diagonal bisects, cuts in perfect half, this angle. I know mine doesn't look perfect, but it does. That's what this means, that the diagonals bisect each other. Diagonals are perpendicular bisectors of each other. What that means is that if you draw both of these, And again, my picture doesn't necessarily look like it. They meet at right angles. All of these lines meet at right angles. All right, so this is number 1, this is number 2, and this is number 3. All right, now, do I expect you to remember all of this? No. Do I wish you would write it down? Yes. Am I going to point out to you where this information is in the book? This information about the parallelogram is on page 177. This information about the rhombus is on page 178. Mark this down so that if you need to go back, you can find it. And you might need to go back because the problem that we have requires you to use some of these ideas. Let's explore, shall we? Example 39.3. It's our last one. DEFG is a rhombus, okay? Immediately I think, okay, squish square. So I'm going to draw it. I loved playing in cardboard boxes when I was a little kid. Except, the only problem was, I have 3 brothers, no sisters. They always wanted to like make it totally boy things, and I was okay with that. I was used to playing boy games, but sometimes you just want to do something girly, you know what I mean? I just wanted to make it a nice house for my dolls, and they would not have it, and I never got my way with that. Oh well. Okay, and then John has drawn in both of the diagonals, so I'll do that too. And he's written a bunch of wacky letters in here with degree markers on them, so I know he means all the angles of these. I'm just copying everything. And then he's got out here, he's got a thing like this. And it says 280, like that. Okay. DEFG is a rhombus. Okay, cool. The measure of the reflex angle. Okay, this is the reflex angle. A reflex angle is something just like this. It's like all the rest of the circle. Is 280. All right, Roger. Find all these different letters. All right, one of my hints, besides going alphabetically, is go where the numbers are. So I see this number here. If this much is 280, then we know that a plus x must equal 360, the full circle, minus the 280, the reflex angle. And that is what, 80 degrees? Okay, the two of them add up to 80 degrees, because that would make 280 plus another 80, that is 360. Now, we know that A equals K, because we said that in a rhombus, the diagonal bisects the angle that it comes from. I know, mine doesn't look perfect, but just pretend, okay? So, if A, I'm sorry, this is an X, not a K. That means A must equal 40 degrees, and X must equal 40 degrees. Oh, I feel so good about it, don't you? And again, in order to know this, we had to remember that the diagonals of a rhombus bisect the angles. Now, we know something about what's going on in here, don't we? We know that the diagonals of a rhombus meet each other at right angles. So we know that C also must equal 90 degrees. Right? Now, and we know that this must equal 90 degrees. So we know that A plus 90 degrees plus K, that's all these three, they have to equal 180 because they're in their own little triangle, right? Okay, so that means that A we said is 40 plus the 90 plus K equals 180. This is 130, so let's subtract 130 from both sides. And we get that K equals 50 degrees. All right. Now, what about B? B is on the other side of this bisector. So B has to be the same side as K because they're being bisected. So that means B has to be 50 degrees also. And have we gotten everything yet? A, X, B, K, and C. A is 40, X is 40, K is 50, B is 50, and C is 90. Yay, we got them all right. We did them in a slightly different order. It's fine to do them in a different order. There's no rules on how to do it. I can give you hints on what to do if you feel stuck, but if you're jamming and it's all falling into place, do it whatever order you want, all right? Okay, that problem is a great example of, I think, a fun way to test us on our knowledge of the properties of squished rectangles and squished squares. I don't mind a problem like this. I don't really like lists of boring properties. Puts me to sleep. But that's kind of fun, don't you think? And that's why it's worth knowing them. So again, make sure you get these page numbers, if nothing else. And if you don't remember anything else, remember that a parallelogram is a squished rectangle. A rhombus is a squished square. Squished meaning like the cardboard box you played in. And that a rhombus is everything a parallelogram is plus a little bit more. All right? Yay, lesson 39, done. Okay, this is Thanksgiving week, and I'm giving you mini homework assignments. So the homework for this lesson, which is 39, I want you to do all the practice. I'll slide this up a little. And then I want you to do the problem set. And let me just look really quick. We will do 1 through 15 odds only. Okay, so you're doing 1, 3, 5, 7, 9, 11, 13, 15. Yay! Enjoy your abbreviated homework this week, and I will see you for lesson 40. Thank you.